of movies.
Okay, well if it doesn't work, you can always use your laptop.
Okay. I have a.
You have a stick.
Seems there's a recording of the.
Well, so we have a couple of people who like to watch it who can't be here. That's the main reason.
Oh, I'm totally fine with it.
Okay.
Actually, I want people to have that.
Okay. Yeah, in particular, there's this.
Oh, this is okay.
Yeah, but that's not this. This is just the computer.
Oh, it's really off.
Computer itself is on. We're not getting any signal.
Okay.
Did it come up?
Yeah.
Okay.
That's
Good. The whole folder?
We can open it right away, or you want to copy?
I think I would copy it just because
Yeah.
it's
So
faster.
maybe
Should
then
we
we can.
copy the whole folder or just
Just.
what's Does it need the movie files? Well, let's try it.
Saying unable to open the DTM key because it isn't a valid keynote document.
Are they normally? Okay, well now I don't know anything about Keynote, so now we have to wait for our computer people.
It's showing that image. That means it's recognizing that it's a keynote presentation. There must be something.
Maybe it's the version of Keynote. She said we had the most recent one, but maybe we don't.
Well, it could. Maybe I was using it.
Usually. What if I try to open it? A stick. Well,
From my computer.
yeah, let's try your computer. You could also just tell Casey, ask Casey to call Michael.
Do you want me to open my computer or wait?
Yeah, you can go ahead and try it. I was just looking for this magic sheet of paper that we have that says, so you can connect it here. This might even be the right dongle. So, worst comes to worst.
Yeah.
Okay. I know your movies will work that way.
So should I just keep the...
Well, so let's just, we might as well eject your stick, because I don't think, and I don't want you to forget it. There's your stick. And then when Michael, who's our computer guy, gets over here, we can see if he can make it work. So the problem is, if it's on our computer, then when they broadcast, it shows an inset of you, like a video of you from that camera, and the slides. If you don't use our computer, then it just uses the camera to capture both you and that, and so the quality is somewhat lower. But
so we can try that out actually once you're
yeah.
90%.
Yeah.
Maybe you can
Some more coffee?
I just need some water.
Okay,
So,
water we can definitely do. Oh, there's Michael. So it says it's not a valid keynote file.
Probably run a later version of what's on that.
Okay. Casey had said we had the most recent version, but Casey.
No, it's not on now.
Okay. So now we're on his, this is his computer, which is working fine,
Yeah, yeah.
but I couldn't get the MP open.
So, the solution is running.
See this is still.
Yeah.
is there a way to change my version to the version?
Yeah, so you can export it to an earlier version.
Oh, it's yeah, we can try that.
Do you have any video?
Yeah,
It's going to his content work like that, right? So that's okay. I need your stick back, sorry. There must be a mistake here.
there you go. So now we are on the stick. We want to keep it on. Oh, so the original file. Okay, so we will find that.
Somebody got rabid.
That's where my dog's going to be.
From here, so you don't have to.
No.
Oh, it's opening, I think. It's in progress, at least.
Yeah.
That's better. So, fourth slide is actually a movie. We are not on screens. Prepare. Okay, so if this works, there are other movies that are about similar. Yeah, it just looks it. So there. So we're waiting all the time.
Oh yeah, I'm reading it all really quickly here. I've got it all. That looks a little funny. Yeah, so some of the boxes got a little messed up. And that is covering something. The box.
Maybe I can.
Do you want to fix it, or do you
Yeah.
want to just use your computer?
I'll fix it because there is an advantage if we use rectangles so people can see properly.
Yeah, I don't know how many people watch our stream, but yeah, take some water. Some coffee for me.
So it takes a while. That's looping. Yeah. It's the same one. There you go.
Moment of truth. Oh my God. we won't look yet.
You got my final punchline then.
Good.
Oh, so it's the boxes are the ones that need to be fixed. So maybe you can look at this one.
This is a really full glass.
Oh, thank you.
Oh, something happened with the whole situation, and so they probably installed the how's the Apple? We had to export, he had to go back to his computer and export his, it has an older version, because we don't have the version of it screwed up.
Oh, that.
Yeah.
It's just.
The whole computer was on Monday, so.
Oh, really?
Yeah. But we worked fine, it was just, it didn't have the most recent version. Right. As it used to have the most recent version? Oh, I don't think it ever has. Because, it's. No, I think it did, so we've done yourselves. We all got your side.
Take that down!
Like still sticky. I just stuck it right to it last time. It worked. Hi. I'm Michelle.
Hi, I'm Ravi.
I work at Geophysical Planetary. We're all family here. We're all family.
Sure. Good try. I'm just trying to fix fonts here.
Yeah.
Things.
The last year's all set up, so there you go.
This is extreme.
Is Zara coming to the talk? Zara? Okay. Next time.
So this is live stream. It's not.
Huh?
Oh, I did. Absolutely. There's nothing. Keynotes. So when if so will my target okay, so what kind of this one? So maybe I should save this one since I made the changes. So now it's saved. Even if it's crashed. So we'll do like that's fantastic. That's it. Thank you so much.
Thank you. I'm sorry.
No problem. Is there laser pointer? Yes. Can everyone hear me? I'm just hanging around outside for a second.
Okay.
Thank you.
That things is just for the first software that I go.
I'm not sure what it's for. I think
The
if you're
sound
out,
is-
if you're outdoors, I don't think it has
Well,
any real
it looks like, okay.
It looks nice.
Yeah, well, it doesn't make that difference. You can buy soft.
Yeah.
Check the package that came.
Yeah, it's fine.
It's
Yeah,
fine,
so
yeah.
I just put it in the, next to the printer
Oh, okay, whatever, you know,
Right.
because you're doing the work, yeah.
when the message
Actually-
comes that it has to be replaced, you put it.
Oh, okay, so this is not badly needed.
But it has a warning now that it's going to.
Okay, yeah, because,
It'll probably happen in the next round.
because,
So
yeah.
sure, the USB stick we should keep it attached to it.
No, did I give it back?
Okay,
Did I
maybe.
give it back to you?
I did, yeah.
Yeah.
Okay. least worried that would be origin, so, but
Yeah, that's it.
Thank you.
Okay. Yeah, no, it'll be
that should be,
replaced
yeah,
the next
okay,
one.
yeah, I knew if you didn't say urgent, so wouldn't be. So maybe it's like,
long time, it was 1963.
66 or something?
Yeah, mine was a 64. No, but it was
Well, Mike was here to help taking.
it was food.
Oh,
you
the
know?
picture is here, sorry. I also wanted to say, this,
Yeah, Mike said what she works. Yeah, the something part, the Mike.
oh, my picture, oh, so maybe you did it. Okay. Yeah, it broke, so I just thought maybe you said
Yeah, I finally
well, I don't know about that.
finished the open.
Did you finish it or did you give up on it?
No, I finished.
Yeah, but he gets
You know, what you should have done is
I know, you
Okay,
told me.
thanks.
spread it to the whole.
I know.
I should have done a chair.
I just didn't feel that it was worth it. With regard to those ringlets are so much of a pain in the neck.
But you don't have to do it with ringlets, you can do it with thread in your arm or something.
Sure.
You have to wash these glasses, these new glasses.
You get the lens wipe.
Yes, I gave you a lens wipe. I just need to make sure I know where they are at all times. I mean, I have 2 pairs of glasses in that house somewhere. I can't find them.
I'm sure they're not gone, I'm sure they'll turn up.
Well, they'll turn up eventually, I guess. I sure hope
So it's
they don't.
my pleasure to introduce today's DTM speaker, who is Ravi Kopparapu, who is visiting us today from Goddard Space Flight Center. Ravi did his bachelor's and master's degree originally in India and then came to Louisiana State University. And I thought, well, that's an interesting choice for someone who wants to study exoplanets. Why Louisiana State? But of course, if you've been keeping up with the news from, say, yesterday, Louisiana State is in fact a hotbed of one particular very exciting new form of astronomy, which is LIGO and the detection of gravitational waves. And so that is in fact what Ravi worked on for his Ph.D. and then went to Penn State as a postdoc working on that. But as you just told me, he wanted to study a subject that he could explain to his mother. And in, what year did you go to Penn State? 2010, something like that?
Yeah.
2000? It wasn't clear that there would be a detection of gravitational waves anytime in the near future. And there was this beckoning field of exoplanets, which is, of course, extremely exciting. And so we are lucky for exoplanets that Ravi switched to studying the nature of exoplanets and what it takes to have a habitable exoplanet. And we're also lucky locally because just this last fall he moved to Goddard from Penn State and is now a research scientist at Goddard, so he's also in our neighborhood and can come over easily and visit. So thank you for coming, Ravi, and we look forward to your talk.
Oh, thanks, Alicia. You can all hear me. Right. Okay, great. So I changed the title of my talk here. It used to be the search for potential habitable worlds in our galaxy, and I removed the search for because as you will see, we'll know some potential habitable worlds in our galaxy now. And I'm going to stress on potential a lot in this talk because then hopefully in the near future I hope to come back here and give habitable worlds in our galaxy, and so we'll know for sure at some point. We know at least one now. All right, so I just want to acknowledge my collaborators. Some of them you probably know, and some of them work at NASA, and they have been really important. I'm part of the VPLT, Virtual Planetary Laboratory. It's a virtual team based at the University of Washington, led by Victoria Meadows, the professor at University of Washington Department of Astronomy. And we have a lot of collaborators there. I believe maybe some of you are in the audience are also part of the VPL team. So it's great to have fun with lots of people. Once I move, LIGO is fun too, but it's so exciting to be in this exoplanet field.
You ought to be able to discover a lot of worlds with all those people.
Oh yeah, some of them have already did. In fact, these people, these are the observers in radial velocity detection techniques, and they have got a
recently awarded by NASA and NSF together to build an instrument to find Earth-sized planets, small planets around the F2, FGKM stars. So there are some people who did discover some exoplanets here, unlike me. All right, so coming to the detection part of the exoplanet, this is a standard slide everybody shows when we are talking about exoplanet discoveries, and this is the year of the exoplanet discoveries and how many detections are there made over time. And the red histograms here show a detection technique called the radial velocity. I just mentioned it's a technique that is being used to detect planets around other stars with Doppler shift orbital of the spectrum of the star. So you take the spectrum of the star and see how the spectrum is oscillating, because the planet and the star are moving around the center of mass, so the star would also be moving back and forth, and so you'll be able to find planets based on that. And you can see that Paul Butler is one of the pioneers of these radial velocity along with Jeff Marcy. And so during the initial discovery phase of exoplanets, you'll see most of the exoplanets were discovered with radial velocity detection techniques, and Paul Butler played a really key role in that. And just after Kepler mission, you probably have seen these news articles over the last few years that Kepler found these many planets and Kepler found that planet and so on. Kepler, after launch of a Kepler mission, you can see the green histograms have increased. That's that detection technique, something called a transit technique, which I'm going to talk about in the next slide. And Kepler really opened up floodgates of discovery of exoplanets, and you can see them. They have been validating planets in the last 2 years in thousands. So as of now, if I remember correctly, there are about more than 2,500 or 3,000 confirmed exoplanets that we know. Just imagine, just 20 years ago when I was just entering into college, that we knew probably one exoplanet. That's about 51 Pegasi b. And now in 20 years, we know about 3,000 exoplanets around us. So this is an amazing discovery space and discovery frequency of this field. And that's the reason why I got so excited, because you know what? Hollywood also helped me, because aliens, right? So, all right. So the green histograms here are the detections from a method called transit method, where you have a planet crossing in front of the star, blocks a part of the star, and then if you trace the brightness of the star, you can see there's a dip because some part of the star light is blocked. And the amount of the dip in the light depends upon the size of the planet. A larger planet blocks a larger amount of area of the star surface. So based on this, there have been many detections. In fact, Kepler just dominated all of those discoveries in the recent years. And with these detection technique, we can get the size or the radius of the planet. And then the one I talked about, the radial velocity method, we can actually get the minimum mass of the planet. And so if we have both observations from radial velocity and transit method, we would know the mass and the radius and the density of the planet too. Okay, so all right. So what are the different kinds of planetary properties that we can say something about the exoplanets? Well, this is a histogram plot again. This on the x-axis is the size of the planet. So these are all Jupiters and Saturns and Neptunes, and these are all Earths and super Earths, slightly larger planets. And these are some planets in between. We call them mini Neptunes, mini super Earths, or super mega Earths, or whatever it is. But we don't have those kind of planets in our solar system. And as you can see, this gives you the number of planets with respect to the size of the planet itself. And most of the planets we have discovered now not most of them, many of them have are Jupiter or Neptune-sized planets. And as you can see, even though we are very sensitive to those kind of planets, larger planets make block a bigger amount of star surface. There are not, we don't see a lot many of those planets here. the reason that probably indicates that, you know, our universe is probably not, or at least the galaxy is not making them many more of those larger planets. So it's an astrophysical constraint on it, which means that, you know, they may be, that's all, we detected most of the planets that we are able to detect with this Kepler mission. And also you can see these are Earth and super Earth planets, and they are a little lower in number. The reason for that is because it's really hard to detect these tiny planets in larger, longer orbits. And so even though they may be more, and we think there are more of them than compared to Jupiter-sized planets, we still maybe it will be difficult for us to detect these kind of planets because the signal-to-noise ratio is too small for these small-sized planets. And by the way, Kepler is observing most of the stars. Kepler is observing sun-like stars, so it's even harder to detect these smaller planets because they will be blocking a smaller surface area of the star, and so that also factors into this. Okay, so now we know that there are a lot of smaller planets. There are a lot of super Earth planets over here, and there are a couple of sub-Neptunes or mini-Neptunes we call them. So what we wanted to see is that what could be the composition of them. So this is a slide that a graduate student from Penn State I was working with created. So this is on the x-axis, is the mass of a planet in Earth masses. So it's 1 Earth mass, 10 Earth mass, 20 Earth masses, and the radius of the planet in Earth units, again, 1 Earth radii, 2 Earth radii, and so on. And then what we wanted to see is that what could be, we plotted theoretical models of the composition of a planet which is pure water and pure rock here. And so we wanted to see, okay, if you try to put solar system planets on this plot, where would they be? And since we have, and we didn't do Jupiter or Saturn, the gas giants, because they would be somewhere over there, because they are hundreds of Earth masses and they're quite large in the size. And so we just focused only on the ice giants, and the next one we have, the smallest one is Earth. And so Earth would fall somewhere close to or in between the water and the rocky part of the graph. And you may not be able to see from there, but there's a little water bubble over here. So if you try to collect all the water and try to make it into a sphere, that's the amount of water Earth would have right now. And so it's more closer to the rocky composition than to the water composition curve over here. Okay, so these are the only two kinds of planets we have now, ice giants and Earths. But if you plot the exoplanets on top of them, they're all over the place. So they are many of these smaller than ice giants and larger than Earth-sized planets, and they have all sorts of compositions over here. In fact, one of them actually is right over here. It's an extremely dense planet. So it's an extremely large mass, but also has about Earth size. We don't know what kind of a planet that is. It could be a core of a star, a core of a planet, or some kind of weird planet that we don't know. But I have to caution here that I am not showing the error bars of the detection of mass and the radius here. So there could be a huge variation in their mass and radius measurements at some point. Okay. And if we want to see what the kind of planets that can be on these water or rocky curves, I would say, so this is again an image generated by that grad student. What we think is that if you have a pure water planet, you probably can have a core and some kind of different phases of ice inside, ice phases of layers inside the planet, and then probably some kind of a hazy atmosphere. When I say hazy atmosphere, it's not made of haze or anything. It's just some kind of water vapor atmosphere, probably. And if you look at the same way for a rocky composition planet, you can probably get different layers of rock types within the inner core, from the inner core to the crust. But then you probably won't be able to see much of an atmosphere for that kind of a planet, for a good reason, because these planets, so these planets, for example, this planet is more massive than this planet over here, the blue one. And so larger mass planets have smaller scale height. And so they would be, the atmosphere is much closer to the, it's not much spread out from the surface, and so it would be hard to see these atmospheres of these planets. And that's another reason why it's difficult for us to see if we can find out the composition, the atmospheric composition of these smaller rocky-sized planets, because they would be smaller, and so the atmosphere would also be, the scale height would also be smaller. And so it's hard to find the composition of these one, atmospheric composition of these kind of planets. Okay, I'm going to skip that one. But until now, I didn't talk anything about how far the planets are located. So in the previous plots, all I showed was that, you know what, I know the mass of the planet, I know the radius of the planet, but then how far is the planet from the star? Because it depends on how much light the planet is receiving, and what can we say about the composition, the water composition, or the surface or atmospheric composition of the planet. And so what we tried to do was that we tried to put the composition or the incident flux on the planet as compared to the Earth, and see how different kinds of planets look like, exoplanets look like on this mass radius plot. So the scale here is 1 means that the planet is receiving exactly the same amount of the starlight the Earth is receiving from our current sun. And this is a log scale, so 1000 means that the planet, any planet with that color scale receives about 1000 times the flux the Earth is receiving from the sun. And so you can see this is like a crayon colored plot of exoplanets with how hot they are essentially. And you can see Earth is over here. I was actually, when he generated this plot, I was like, oh, whoa, this is a cool planet, what is that? And that turned out to be Earth. And so, well, yeah. And so that's Earth is over here, and then look at this planet. This is it's off the scale actually. Oh, maybe about 10 to the 7, or about 1 million or 10 million times. There's something wrong with the measurements over here probably, but it's super hot. It's a very hot planet, about the Earth size, but has a very low mass. So it's probably an evaporating planet. So that could be because it's receiving an enormous amount of starlight from its host star, which we have to find out what kind of a star it is. But then looks like it's pretty close to the star and probably either disintegrating or spiraling into the host star itself. And so this gives you an idea about how hot or how cool a planet would be based on how far the planet is from the host star, and also what's the size. This gives you an idea of where to look for Earth-size or Earth-like planets just based on the observables of the distance from the star, the measurements of mass, and the radius. Okay, so that's an important point because we want to see where these planets are located in. Just to give an example, the Kepler space telescope, the Kepler mission, is actually looking within only a small part of our galaxy. And all 3,000 planets that I just talked about are at the most 3,000 light years away from us. On an average, I think a Kepler planet distance is about 400 to 500 light years or so. And so the larger planets, in fact, if we go to further away, far distances here, we would probably be seeing more larger planets because those are the ones that can be that can give a good signal to noise ratio or better signal. And so most of the planets that we discover are on average about 300 light years from us or 400 light years from us. And that's only a small part of the galaxy right here. And so what Kepler team and people who work on the Kepler data do is that they collect this data, try to estimate how many more planets that we are missing from the galaxy. First of all, from the transit method, because if the planet is not crossing in front of the star, or it has a different inclination angle, we may be missing that transit, right? So they take into account that the statistic, and also they'll see how many planets we are missing, and how many of them how many stars are representative of that kind of planet are there within the galaxy, and they come up with a number and say, you know what, this is how common these kind of planets are. And that's an important thing to do because we want to know, well, at least I'm very excited to know how common are Earth-like planets in our galaxy. And so Kepler mission, if we have more data of more planets, we can figure out how common are Earth-like planets, not just Earth-like planets, how common are other solar system type planetary systems. And so that's one of the goals of the Kepler mission. I'll come back to that in a second.
Can I ask a question?
Yeah, you want me to go back to
Yeah,
that?
back 2 slides. What does this, on the previous diagram, what does the size of the dot represent?
I forgot to say that. Size of the dot is the radius of the planet. So a larger size is a bigger planet here.
Question as well. How do you measure the radius of mass?
Okay, the radius is from the transit observation of the planet, and the mass measurement, okay, so ideally the mass measurement should be from the radial velocity technique, where you can see the wobble of the star when the planet is going around it. But I think for these Kepler planets, what we did, I think, is that we used a mass radius relation, a theoretical mass radius relation to generate the masses so that we can put them on this plot.
Yeah, because Kepler doesn't measure mass.
Well, Kepler doesn't measure masses, but there is also another issue, is that in order to follow up on all the Kepler detections to measure the mass of those planets, because Kepler can only measure the size. So then we have to go back to our telescopes and use radial velocity technique to re-observe those planets and determine the mass. And the enormous amount of time we can spend, it would be huge, because we can't catch up with Kepler discoveries with the ground-based observations of radial velocity. Okay, so essentially what I'm saying is that we need more telescopes.
And more astronomers.
More astronomers and more telescopes, there you go. All right, so why are we interested in these incident flux on the planet? Well, we want to find the potential habitable planets. We need to know where to look for them, so how far they are from the star, and what do we do after we finding potential Earths, and how do we select those candidates to observe potential atmospheric signatures that we can say, you know what, this planet can have, has some kind of a biosignature on it, or some kind of life on it. So why not just find those planets that receive the same flux or same light as our Earth around other stars? What's wrong with that? I'll come back to that in a second, the slides. And the most important thing is, how common are our potential habitable planets? How far in the solar neighborhood do we have to look to find one of these habitable planets? So there is actually a possible path towards answering that question, and so that I'll come to that in the next couple of slides. Okay, so to answer some of them or to cover many of those questions, we needed to define something called a habitable zone, which is the region around a star where a terrestrial size or mass planet with suitable atmospheric conditions can maintain liquid water on its surface. Okay, so when I say suitable atmospheric conditions, it is probably most likely a nitrogen-dominated oxygen atmosphere like our Earth right now. And so we are looking for Earth-like planets around other stars. And some people may ask, why Earth-like? Why can't we find some other different kinds of planets? Because that's the only planet we know what to look for. We don't know, at least we can't figure out, we reasonably know right now what kind of a biosignatures Earth can produce. Based on our satellite observations, we can actually go back and look at Earth and see what kind of gases are there. So we try to look for those kind of signatures. So it's a good starting point. And so it's a nice way to start looking for habitable planets. And there was a question on why did you define the habitable zone in this way, the region around a star where a planet can maintain liquid water on its surface. Well, the insistence on the surface is because there have been questions on this one too. This definition of habitable zone has little to do with the habitability. Doesn't mean that the planet is habitable. Okay, so it's a subset of a larger definition of the habitable zone where life can arise irrespective of the detectability. So for example, if someone says, you know what, Europa has or may have subsurface oceans and there could be life on it, well, that's great. We can send missions to that, and possibly if you get enormous amount of funding, we can dig through it and find out if there is life under the Europa or not. But we have that luxury to do that within our solar system. But for exoplanets, at least in my lifetime, I don't think there's going to be one. And so we need to look for signatures of life remotely using our telescopes. And for that, we want to focus on the surface liquid water condition. And the reason for that is that life on Earth requires liquid water during at least part of its life cycle. And the assumption is that if you have liquid water on the surface, then life on the surface would be interacting with the atmosphere, and then that, based on that, the atmospheric signatures, we can observe remotely that an atmosphere is of a planet, and then potentially conclude or come up with a solution of whether that planet can be habitable or not. Okay. So surface liquid water criteria is only for, the way I define the habitable zone is only for remote detection purpose. Okay, so I want surface liquid water because I think there could be life on the surface which can interact with the atmosphere, and so we can detect it remotely. Okay, and Kepler actually has one of the primary goals of Kepler is to find the habitable zone planets. Goal 1 is habitable zone planets, and not only that, to determine how common are these terrestrial habitable zone planets are. And there is a reason for that, because we want, once we know how common are Earth-like planets, then we can come up with an estimate of how far we have to look within our solar neighborhood to find a nearby Earth-like planets around a sun-like star, and then we can come up with some kind of a designs of future big space telescopes that can look for these biosignatures. And so finding this number, Kepler, in fact, that is the main goal of the Kepler, is to find the occurrence of these potential habitable planets. Okay, so how was the habitable zone defined? This was done way back in 1993. I was still in high school, and at that time, Jim Casting and Dan Whitmire and Ray Reynolds from all of them, they used actually Jim's model, one-dimensional climate model, assuming an Earth-like planet with a water-dominated atmosphere at the inner edge and the CO2-dominated atmospheres at the outer edge, to come up with a habitable zone estimate. Where could a planet can have liquid water on its surface, can sustain liquid water on its surface? And at that time in 1993, there was no exoplanet detected. I should be careful. There was no exoplanet detected around a sun-like star. Okay. In 1992, Alex Wolshan from Penn State found pulsar planets around pulsars, the dead stars, right? So, and a year later, Jim and all published this paper on the habitable zone, and 2 years later after this was the first exoplanet around a main sequence star, 51 Pegasi b, using radial velocity technique was detected. Anyway, so at that time when Jim and all published this result, there were no exoplanets, not even hot Jupiters or any big planets too. But the reason they wanted to do was that at the time they wanted to come up with a criteria of how to find biosignatures on other planets. And the assumptions they made in their climate model is that if you should have a water-dominated atmosphere and the CO2-dominated atmosphere at the outer edge, because the idea was to see that how wide at the minimum, how wide the habitable zones can be. For example, if you take an Earth-like planet and keep pushing it closer and closer to the star, its ocean, it has lots of oceans on it, lots of water on it. And so if you keep the planet and push the planet closer and closer to the star, at some point, most of the water from the surface goes into the atmosphere because it's getting hotter and hotter. And then that results in something called a runaway greenhouse effect. Okay, so that's something what happened with Venus, and so that defines the inner edge of the habitable zone for us. Why? Why is that? Why the inner edge of the habitable zone is where we have most of the water in the atmosphere? Because the definition of the habitable zone itself is that we should have liquid water on the surface. So when you have most of the water in the atmosphere, by definition, it is not in the habitable zone, and that marks the start of the inner edge of the hab zone. So there is this phase called the moist greenhouse phase, where the oceans remain liquid, but the stratosphere becomes really wet in the sense that most of the water goes into the stratosphere, and so it becomes really hot, and so that wouldn't be a habitable planet. And beyond that point, if you keep pushing the planet closer and closer, there comes another climate state called a runaway greenhouse. The atmosphere becomes really opaque to the infrared radiation, and so all the water from the surface evaporates and the planet is doomed. It's doomed for life even before that, but then this is just where all the water goes away. So that defines the inner edge of the habitable zone. For our habitability purpose, for people like us and life like us, the moist greenhouse limit or the water loss limit is the most relevant for the inner edge of the habitable zone. Okay. And then the outer edge of the habitable zone, there is another assumption made in the climate model, which is that if you have a planet, Earth-like planet, and if you are taking it further away from the star, it's getting colder and colder. But then Earth has a carbonate silicate weathering cycle going on. And so as you are taking the planet further away from the star, CO2 starts building up from volcanoes and then trying to keep the planet warmer. And at some point, if you take the planet much further away from the star, there comes a point where no amount of CO2 is enough to make the planet warmer. And that would be the outer edge of the habitable zone. Okay. And so based on these two limits, inner and outer edge of that's called the maximum greenhouse limit, because it's the maximum amount of CO2 you can put in the atmosphere to get a planet to be habitable. So at that time, since it's been 20 years since Jim published that model, so when I joined Jim after my LIGO stint, and Jim said, you know what, we should probably revise that model. And so what we did was we tried to update the model with new absorption coefficients. So 20 years ago, when Jim had that model, water vapor and CO2 were using the absorption, how strong water vapor and CO2 can absorb infrared radiation. The database was older. So we tried to use a newer databases when I got this model, and we started updating. It took me a year of my postdoc too. And it seemed no end at that time, but then it was great. And then when we tried to run the model with that, we came up with a little closer, a little bit scary inner edge of the habitable zone, and the outer edge of the habitable zone did not change much. Why the outer edge changes, we'll talk about it if you're interested. But the point here is that the inner edge of the habitable zone is much further away from the star, or as in it's much closer to the current Earth's orbit than what Jim and all got some time ago. Okay, that's enough with the model. So what are the results right now? Well, what I'm showing here is our results, the new climate model results from the habitable zone. The x-axis here again is the amount of starlight the planet is receiving compared to the Earth. For example, if you see 100% here, it means the planet is receiving the same amount of flux the Earth is receiving from the current sun. And so 75% is that it's receiving about 25% less flux than Earth is receiving from the sun. And vice versa here, it's 175 means it's receiving 75% more flux than Earth is receiving. And these are the habitable zone limits. So just to give you an idea, this is the runaway greenhouse limit here, and that's the maximum greenhouse limit. That's called the conservative estimate of the habitable zone, which means the habitable zone can be at least that wide, if not more. And there's a reason for that too. I'll come back to that in a second. So this is at the minimum width of the habitable zone, and that would be the maximum width of the habitable zone based on some empirical limit of how hot Venus was a billion years ago. And what we plotted here, again, this is the temperature of the star here, effective temperature. So sun is over there, about 5,800 Kelvin, and cool stars, hot stars. And most of the exoplanets, including the ones that Kepler released a couple of weeks ago, are within the habitable zone. Even though I'm showing there are a lot of planets over here, there is a small caveat here that many of these planets are about less than 2 Earth radii. The current theories from different groups are saying that if you want to define an Earth size, that is probably somewhere from 0.5 Earth radii to 1.5 Earth radii or 1.6 Earth radii or so. So anything from 1.5, 1.6 to 2 Earth radii, we can say it as a super Earth, or it could be a mini Neptune kind of planet. So all these planets, some of these planets have larger than 1.5 Earth radii, but less than 2 Earth radii sizes.
Excuse me? So
So what changes at 1.5 radii to make it not Earth-like?
I think it's mostly based on the density measurements of the planet. So when Earth is about 5.5 grams per centimeter cube. So beyond that one, there are different kinds of compositions based on these are all based on the theoretical models. And then so the density variations can say something about how whether it is going to be an Earth or or terrestrial. I would use terrestrial size planets. So I shouldn't probably use Earth.
But you mean, so when it's bigger than that, the atmosphere will be substantially different, or?
Yeah. So I'm coming to that. So right. So that means that it could probably attract more hydrogen during its formation, and so maybe it could be a slightly hydrogen-dominated planet. But we do not have any measurements of the atmosphere for these larger planets. All we know is the density measurements.
I'm confused by the temperature. What temperature is that?
That's the effective surface temperature, effective temperature of the star. So, for example, the Sun is about 5,800 Kelvin, and these are cool stars, 3,000 Kelvin, and so on. Maybe I should write the surface effective temperature of the star. Great.
Stellar temperature.
Yeah, stellar temperature. There you go. So, right now, in fact, this is a curious thing. We were talking about the transits and the radial velocity ones, right? Transits are the ones where the planet crosses in front of the star. Radial velocity are the ones where wobble of the star, we can find out the minimum mass. And even though radial velocity measurement, radial velocity technique existed for the past 20 years, and transits just came up maybe in the last 10, 15 years, or even less than that, and Kepler just did it in the last 5 years. We know only one radial velocity planet that is potentially in the habitable zone compared to all the transit detections that have ever been made. And so this is not I'm not saying that, radial velocity lost or transits won, no. This shows that we need to invest a lot of telescope time to find out or validate or find out the masses of these habitable zone planets, or to invest more in radial velocity techniques for that, so that radial velocity can also find more of these habitable zone planets. It's really hard. Just imagine, if you want to find an Earth-sized planet around a Sun-like star, usually you need to wait for about a year or so, right? Because it's a year's worth of data that you need to take to at least get one orbit. For transits, it becomes even difficult, because if you are going to get only one transit of the planet, it could be anything. It could be a background eclipsing binary that's mimicking Earth-like planets around a Sun-like star. And so what Kepler team does is that they need to get a couple of orbits, which means you need to wait a couple of years to collect the data. And so that's the reason, one of the reasons Kepler's main primary mission was about 4 years. And even then you can see it was really hard, just because of the small planets around Sun-like stars are really hard to detect because the signal to noise is low. Even though we have detected many of the smaller planets here within the lower size star, we do not have many, in fact none, any planets in the Sun, like around Sun-like stars in Earth-like orbits from Kepler data. This is a problem, and that's how nature made them. So we'll need to just collect more data on these longer missions to find these Earth-sized planets around these Sun-like stars. And this is actually, oh, by the way, this is a habitable zone calculator that we have generated to do these habitable zone estimates. It's an online calculator. If you know the temperature of the star, you can get the habitable zone estimates from this online calculator. There is also a Fortran code and also a Python code available. So if you want to do it, you can just go over here. This is just my PR saying that there are lots of planets over there. Okay. This is the inner edge of the Hab zone. So whatever I described to you until now was the work that I did with Jim and other collaborators, but using a one-dimensional climate model. So when I say one-dimensional climate model, it's a model which has only vertical dimensions in pressure or in altitude. Okay. So and then that assumes a global average temperature. But there have been three-dimensional climate model to do this habitable zone. In fact, I should probably put that plot. once I published that one-dimensional climate model habitable zone results 3 years ago, there has been a huge increase in the number of publications of the habitable zone estimates from 3D climate models, including myself, because we immediately realized that that's not enough. Then climate is not a one-dimensional state, and so all I wanted to show from this plot is that there have been some studies. There are some studies which say the habitable zone, this is all inner to the hab zone. That again, it's the same thing. The flux of the instant on the planet, 1 means about the same as Earth, 2 means twice that of Earth. Stellar effective temperature. This is a good plot here. It's great. So you can see that some studies say that the habitable zone is way closer to the star, and this is my 1D model that I just talked about. And some of the points here, some of the 3D models did not do much parameter exploration. So we are still exploring, trying to confirm. What we want to do with these 3D models is what IPCC is doing with the global warming, right? So they have like many different type of climate models, and they compare with each other, and they come up with a consensus estimate of their results. And so we want to do with the habitable zone estimates a similar way. We want to compare all our 3D model results, come up with a consistent estimate, and try to figure out where are the habitable zones. And people have asked, why do you care? Just pick one of them, and why do you do it? I'll come back to that in a second. And in fact, this has some consequences. So there was this paper 3 years ago or 2 years ago where they said that you can have a wider habitable zones if you assume a dry planet. If you have a planet devoid of water or very minimal amount of water, you can push the planet much closer to the star than what our models predicted, because the planet can emit most of the infrared radiation, cannot trap the infrared radiation, and so you can push the planet much closer to the star. And in fact, suggested that the inner edge of the habitable zone could be 0.38 AU, almost the orbit of Mercury. So Jim and I looked at it, and we thought that, well, what happens if we put a Earth's ocean on that kind of a planet? If you do that, you cannot have an ocean's worth of water on a dry planet, but still, let's just assume there is an ocean's worth of planet. You can evaporate that water in about 400 years or so. And so it takes, so even though it's really, we want the habitable zones to be much closer, because those are the kind of planets that we would be able to detect with a good signal to noise ratio. We need to be consistent with our model assumptions to do it, because they have practical consequences. Habitable zone estimates are being used in the discoveries of habitable planets, potential habitable planets, and there would be a future target list for future observations, for in-depth observations, to see if the planet is habitable or not. So we need to, if we have so many of them, which one we would be picking, and which one we should be trusting. Okay, so I'm going to skip this. This is, after that paper was published, there was another paper, before that, there was another paper with 3D models of dry planets, but they came out roughly about the same estimates as ours, so, our results agreed. So this is one of the points that I wanted to raise, is that which habitable zones to use, my 1D models or my 3D models or someone else's 3D models. What is the part? So the question then becomes, what is your purpose? What you're going to do with it? Every model has a utility depending upon its need. And so advances in these modeling techniques means that we are trying to solve this problem, because this is a recent phenomenon that we are finding potential habitable planets. And so what can we use the habitable zones for? Well, we can discover the potential habitable planets around different kinds of stars. For climate science people over here, you can see different kind of dynamics, atmospheric circulation, convection, energy transport. I mean, I'm telling you, planets around M-dwarf stars are the most awesome, but also most dangerous in the habitable zone. But they have super nice and super awesome physics going on. And then the applications of habitable zone also, we can use them to find out how common are Earth-sized planets in our galaxy. And what do we do with that occurrence rates? Once we find how common they are, what do we do? Well, the idea is to use that number for the in the hopes that we can design a direct imaging mission where we can look in the nearby solar neighborhood, take a picture of a nearby habitable planet, try to see the atmospheric composition of a potential habitable planet. So there are actually real-world consequences to where the habitable zones are. So what are those numbers that we were talking about? How common are potential habitable planets? If we divide the space into cool stars and everything else, or all the sun-like stars are a little cooler than sun-like stars. My font is a little bit gone over here, so I'm going to put a block here. So for M dwarf stars, they should be M dwarf here, the cool stars, the current conservative limits are about 16%, which means about, if you take all the red dwarf stars in the galaxy, about 16% of them have Earth-sized planets in their habitable zones. Okay, and red dwarf stars are the most dominant stars in our galaxy, about 77% of them, right? So there's a huge number of them in the habitable zone planets around red dwarf stars. For G, which is like our sun, and K dwarf, somewhat a little cooler than our sun, orange kind of stars, the number is now changing anywhere from 2 to 22%, an order of magnitude. And that has become an issue because the whole purpose of Kepler mission is to find that number. G and how common are Earth-like planets in the habitable zones. And so we are trying to see why different studies are not agreeing, and how these numbers, why these numbers are varying together. So hopefully we will know what would be an accurate estimate of these value of eta Earth. It's called the fraction of stars with at least one rocky planet in the habitable zone. Okay, so this number is somewhat critical right now for direct imaging missions that I just talked about.
I don't see how you can even make a rough estimate of that number without more data.
That's exactly right. And so that's the reason we changed the scale rather than we actually trying to detect this one. Because if you say the Earth-sized planets are anywhere between 0.5 to 1.5 Earth radii, we have lots of detections of 1.5 Earth radii planets. Okay, but none of them are in the habitable zone. So it's going to be an extrapolation of the current data to come up with this number, and that is reflected in this large variation of this eta Earth. Okay, this is a slide I stole from Natalie Battaglia. She's from the Kepler mission, and what she's showing here is that this is not a published result yet. This is a slide she gave a talk at some point. Again, she's showing the habitable zone, temperature of the star, amount of starlight on the planet, and and according to her values, about 25% of the cooler stars, depending upon where you cut off cooler, have planets in the habitable zone, rocky planets. About 36% of the sun-like stars have planets in the habitable zone. About 10% of somewhere in between K stars have planets in the habitable zone. But if you look at the error bars, they all overlap. So the weighted mean is about, if you want to say, if someone asks you how common are habitable planets, you say 15%. Okay, 15% of stars in our galaxy have a planet in the habitable zone. I'm being very specific there because we don't know if they're habitable. Okay, the reason and where do we use this value of this occurrence rate or the frequency of this one? This is a plot from Chris Stark. I just don't want to go through it completely. What he's trying to do here is that, if I want to design a direct imaging telescope, let's say if I change the mirror size, for example, Hubble's Space Telescope is about 2.4 meter. JWST, that's trying to be launched in the next 2 years, is about 6.4 meter class telescope. But if you consider a direct imaging mission, which is in the 10 to 15 meter class telescope range, then how many planets would you be able to detect it? And if you do that, that comes out to be about 500 planets or so. And so apparently there has been an estimate a couple of years ago that every star in our galaxy has at least one planet. Doesn't matter if it's Earth-sized, Jupiter, Saturn, whatever. It has at least one planet around it. And so if that's the case, then we would be able to find about 500 planets with our direct imaging telescope, including Earth-sized planets in the habitable zone. And so that's an important number to come up with. So what are the different kinds of direct imaging missions we have? Recently, in the last 6 months or so, there have been 2 concept studies initiated. One is the LUAR, it's called Large UV Optical Infrared Infrared Telescope. And the other one is HABEX, the Habitable Exoplanet Imaging Mission. The only difference between, well, not the only difference, the difference between these two is probably most likely the mirror sizes of the direct imaging mission, and also the kind of technologies that we want to use to find these planets. The animation that we just saw, something called the star shade, where it's like a petal shape and it opens up, tries to block the starlight, and you can see the planets going around the star. Okay, and the same thing here, where is the internal coronagraph. Again, the same method, where you can block the starlight and then try to see a planet around that star. And so there are teams that are studying these 2 technologies and what kind of science we can get from these 2 different kinds of mission. And the goal is to provide a report to the decadal committee in the next couple of years, so that they will, along with these 2 missions, there are 2 more missions. There are far infrared surveyor and I believe an X-ray mission too. And so there will be 4 missions considered in the next decadal survey, and they would be able to figure out what would be the next flagship mission coming out of the 2020 decade. Okay, and Kepler is really helping in discovering these potential habitable planets, so hopefully one of them would be selected. And this is when I talk about biosignatures, these are the direct imaging biosignatures that we would be able to hopefully differentiate between different kinds of planets. If you have a Venus-like planet, if you want to find it, then you would see a big CO2 signature there from the atmosphere. Earth has lots of it, lots of ozone, water vapor, and carbon dioxide, and perhaps we can even detect methane. Methane could be generated, well, methane is generated biotically, so it's probably a very good sign of a life signature. But we need to find other gases also in the atmosphere to say if it's a habitable planet or not. Again, for Mars-sized planet or Mars-like planet, I would say, you can still see if there's a big carbon dioxide signature, probably it is not a habitable planet. So we can differentiate between habitable and inhabitable. Not habitable planet, not inhabitable. And the best part of that is that when you are actually looking at the planetary system to take find a biosignature of Earth-like planet, you would be able to you'd be getting data from other planets in the system too. So it would be an additional a side opportunity for us to do other science which is not related to habitability. Okay, what are the near-term missions? These are all long-term, but the near-term mission are the Transiting Exoplanet Survey Satellite. That's coming up in the next year, is supposed to be the planned launch. But the idea is that, again, it's a transit mission, the planet is blocking the star, and it's an all-sky survey, so it's going to go look at everywhere around the sky, and at a time, I think each field is about 2 months in duration. So this is going to find a lot of planets in the nearby solar neighborhood. And just to give you an idea what kind of orbits that it's going to do, in the field, which means it's going only around, that's about, TESS can find planets within the habitable zone that have orbits about 13 days or so. In the ecliptic poles, when I say ecliptic poles, you can see these overlapping regions on the top. They will have more observations because at each field when you're going, you can have overlapping field images, field observations. And so you can have more data coming from those top regions. And so in those regions, TESS can find planets in orbits in the habitable zone about 175 days, so roughly around mid-K dwarfs to late G dwarf stars. So, and the reason for why it is important is this because TESS can provide target systems to JWST, which is coming up. JWST is not an exoplanet mission, it's actually an astrophysics mission that can also do exoplanets. And so JWST can do transit spectroscopy, which means it can see the light coming through the star to the planet's atmosphere and try to figure out what kind of a composition the planet's atmosphere can have, and then see if it is a potential habitable planet or not. And so the way it does is that different layers of the planet has different composition, and so different compositions absorb in different wavelengths. And so, and you can measure the transit depth based on these different layers, and that gives you the information about where, what is abundance of the species of the atmosphere, and see what kind of species are there. And JWST can do mostly M-dwarf stars, the cooler stars. And so this is for smaller size planets, smaller size stars. We're going to skip that, but I want to come to this one. It's called the movement of truth slide. So I was attending a meeting 2 weeks ago at the other DTM center at the P Street, and one of the speakers showed everyone this slide, and this is when it actually hit me that with JWST we have about 20% telescope time to spend on exoplanets. Okay, and then within that time it can perform one of the following. Either it can do 150 planets with transits and eclipse, or 25 planets with phase curves, or search for lives on 3 temperate terrestrial planets. And if you, this is really important, because if we have several targets that we want to follow up on with JWST, we need to choose one of them. And how would you do that? And because it's an expensive telescope, and so telescope time is expensive there. So on which planet would you be able to spend time on? So this is where the habitable zone or the target list of habitable zone planets comes in, right? You need to, your models better be right. And you know, when you are suggesting or requesting for telescope time to go and observe, spend most of your telescope time on this kind of a planet, we need to be really sure that these planets are in the habitable zone, or potentially habitable. Okay, so this is where we are trying to lead our projects and our work to help astronomers to find out or narrow down the list of planets that they can do a follow-up studies on. Again, take-home points, the same thing I just mentioned. Modeling, like I said, modeling needs to be come together and try to come up with a unified model of the habitable zone estimates. A planet within the habitable zone may not be habitable, but it will be the first cut estimate of where we want to look for life on other worlds. So I'd like to leave at this point and take questions.
Oh, lots of questions. Larry.
So in your last slide, you indicated it would take 100 days of JWST time to search for life on one of these planets. What does that mean? How are you searching for life on that planet with JWST?
Okay, so is this the one you're...
Yeah.
Okay, so...
What do you mean by search for life? What would JWST?
Okay, so they are not saying they can find life on those planets. These are all for planets around M-dwarf stars, cool stars. Okay, so it's the biosignature detection when we say that. So what kind of a biosignatures we want to do it? We want to probably get oxygen, ozone, methane, nitrogen, or some kind of minimal water vapor, not too much because it could be too hot. And so these are the biosignature detections that we are planning.
John?
Yeah, so when you talked about the GCMs, there were some groups that found that the inner edge of the habitable zone moved in quite a lot. What's the different physics that causes that?
Okay. Let me go to that slide. I know you're talking about...
Compared to the one being on.
Positive.
I guess... Oh, there you go.
Yeah.
This one?
Yeah.
Okay. So these, in fact, I should probably write here, the inner edge of the habitable zone here assumes that the planet is synchronously rotating. Okay, so it is not a rapid rotator like Earth. Earth has a rapid rotation. It's a 24-hour orbit, rotational period. whereas the models for the inner habitable for this one assumed that the planet is a tidally locked planet in synchronous rotation around the host star. And at that point, what happens is that if you, and they assumed, and we also assumed, a water-dominated planet, an aqua planet. Okay, so it's mostly water. The reason, and what happens then is that when you have a tidally locked planet or synchronous rotating planet with a water-dominated atmosphere, water-dominated planet, then you would have substellar clouds building up because the planet is always facing the star, and so it's going around the star. But then there would be a lot of ice, water ice clouds building up over there, and then would reflect away, increasing the albedo essentially. And so you can push the planet a little bit closer, still maintaining clement conditions on the surface of the planet. And that's why you can have a inner habitable much closer according to these models.
So when you go to the GCM, you're introducing a lot more free parameters than you would in 1D model. So you've got, like you say, the spin period and the obliquity, the land to ocean volume. You're introducing a whole lot of more variables that we don't know. So that would also mean that you're going to get lots of different definitions of the habitable zone depending on how you choose those numbers.
You are more correct than you really nailed the point down on that habitable zone estimate of the GCM modeling estimates. Okay, and that's right. There are different variable parameters that we can tune and say, you know what, this is how the habitable zone is going to be. Okay, so but then we try to, some of us try not to do too many parameters and try to stick to as close to Earth conditions, because that's what we are trying to look for these with these targeted planets, and then slowly deviate from the predetermined parameters. So for example, if we want to do, we probably won't know the obliquity of a planet from these remote measurements, or from the transit spectroscopy, or transit method, or the radial velocity method. So assuming an Earth-like obliquity as good as any other obliquity measurements, right? At this point, because this is all we know right now. And the other thing is that we know, at least for planets around N-dwarf stars, they are most likely tidally locked or synchronously rotating, because the habitable zone is so close around these stars that they have to be in a tidal locking phase. And so, which means that it is a good assumption to assume around N-dwarf stars that these planets are tidally locked. Whether you can do the same thing for stars that are even hotter than that is a different question that have to be done by some other models. But then constraining ourselves to some set of models which we think are reasonable, and then slightly deviating from that is what we have done. We, in the sense, when I say we, it's not just us, but other groups also. So when we try to provide habitable zone estimates, when I say these are the habitable zones, then that means that those are the habitable zones that we can provide with assumptions as close as Earth to the Earth. So that's the only thing we can do, because at the minimum we will know only the orbit of the planet or the size or the mass of the planet, nothing else at this moment for Earth-sized planets around other stars.
Ravi, what about following the stellar evolution too?
Oh, those are called the continuous habitable zones. So as the star evolves, the brightness of the star also increases, and so at some point Earth would not be habitable. In fact, in the next 100 million years or so, most of the it will be too hot. And so there are, if you're asking about evolved stars or slightly evolved stars, or
well, I'm asking what happens to the inner edge of the habitable zone as you follow a star from, say, 100 million years to, you didn't put that slide.
I used to have that animation. I'm so mad at myself that I didn't.
That's okay.
Okay, so what happens is the inner habitable moves out away from the star, because as the star is getting brighter and brighter, and so the place where you can have liquid water or clement conditions around the star moves further and further away.
But for the M stars, you're actually more luminous at 100 million years than you are at a gigayear. So it's the opposite direction, right?
That's right. In fact, okay. M stars, after they come on the main sequence, they don't evolve much. So they just stay there for billions of years. And so, for them, at that time, it's not going to be a problem. but they have a problem. In fact, there is a question now that is it worth looking for habitable planets around N-dwarfs and cool stars, right? Because of the point that you just made, that N-dwarfs are more luminous during the pre-main sequence evolution, and if you have any habitable planet with lots of water at that time in the pre-main evolution phase, then all the water probably is gone away, and even if you now look in the habitable zone of N-dwarf planets, probably you would find most of them dry or